Chapter 1 is Introduction. Background. The drum tilting and lifting mechanism is a device designed to efficiently and safely handle drum of various size and weight. This mechanism is commonly used in industrial settings such as a manufacturing plant, warehouse, and chemical facility. It allows for the easy maneuvering of drums, enabling workers to tilt and lift them for transportation, storage, and processing purposes. The mechanism typically consists of a framework, hydraulic system, and control to ensure smooth and controlled operation while minimizing the risk of workplace injuries. Objective: able to understand the working principle of drum tilting and lifting mechanism, able to apply and adapt knowledge from classroom lecture to the project and practice engineering skill. Scope: to complete design, analysis, calculation, report, and demonstration. The program for this operation is MATLAB, Google Docs, and Microsoft Excel.
The theory behind drum tilting and lifting mechanisms encompasses a range of engineering principles and concepts that are essential to understanding how these systems work. These mechanisms are designed to handle and manipulate heavy drums and barrels efficiently and safely. Drum tilting and lifting mechanisms involve complex motion, including rotation for tilting and vertical displacement for lifting. Kinematics is a study of motion, including parameters such as displacement, velocity, and acceleration. Understanding the kinematics of this motion is crucial for designing the mechanisms. The theory we derive from kinematics theory is velocity analysis and acceleration analysis. First one, velocity analysis. From the equation, we know that Vp is equal to velocity of point P along x-y-z axis, or point being observed. VO equal velocity of point O in XYZ axis, concerned that the point O in XYZ axis is observer. V relative is the velocity of point being observed with respect to the observer point. Omega is angular velocity of XYZ axis. R is distance from point O to point P. The another theory is acceleration analysis. From the equation, we know that AP is absolute acceleration of point P as a point being observed. AO is absolute acceleration of point O as an observer. A is relative acceleration. 2 omega cross V is Coriolis acceleration, which is perpendicular to V. Alpha is angular acceleration of observer O. Alpha cross R is tangential acceleration, which is always perpendicular to R. And last one, omega cross R is centripetal acceleration, which is always parallel from R to point P to point O.
In force and torque analysis, we use Newton and D'Alembert's equation of motion to calculate. D'Alembert's principle is an equation of Newton's by assuming force and torque since inertia has a different direction with centripetal force and angular acceleration of that path. In calculation by using superposition, use the hypothesis of no friction in mechanism force that calculate to make a mechanism has mass and inertia in each part will get together and it will have the same effect as normal calculation. In static equilibrium is to ensuring the mechanism remains in static equilibrium is critical for safety and stability. Static equilibrium analysis helps determine the force and torque required to balance the system at rest and in various positions during operation. This analysis helps prevent tipping or instability. Next is visual work. Visual work is a method used to calculate for the force or torque of mechanism in equilibrium. It is used together with D'Alembert's principle. The most important is that there is no friction. Next is functionality. Drum lifting and tilting are essential operations in industries where drums are used for storage, transportation, and processing of materials. Specialized equipment is employed to perform this function safely and efficiently, contributing to overall workplace productivity. And for the principle of the mechanism, in lifting mechanism, a lifting mechanism is employed to raise the drum from the ground to a desired height. This mechanism may involve hydraulic, pneumatic, or electric system. Hydraulic systems are common and consist of a hydraulic cylinder connected to a pump. When the pump is active, hydraulic fluid is pressurized, causing the cylinder to extend and lift the drum. And for the tilting mechanism, is responsible for adjusting the orientation of the drum. It allows the operator to tilt the drum to a specific angle or position as needed. This mechanism mechanism may also be powered by hydraulic, pneumatic, or electric system. For example, a hydraulic cylinder can be used to control the tilt angle.
And calculation. In this slide, you will see a given data of range between each point and a drawing of mechanism. In the drawing, we have a total of 6 links. Next, we talk about angular. An angular, we assume an input angular as 60 degrees, and we use a given data and the input angular to calculate for another angular. Next, velocity analysis. For velocity analysis, we have total of 5 points that we use in calculation. It's point A to point E. That means we will get velocity from point A to point E, and omega or angular velocity from point A to point E as well. And acceleration analysis, same go to the velocity analysis. We have a total of 5 points that we use in calculation. That means we will get an acceleration from point A to point E, and angular acceleration or alpha from point A to point E.
In this slide, direction force, we draw a free body diagram of link 2 from O2 to A. To calculate for AX and AY made for the link 3 from point A to point B to find BX and BY. We draw a free body diagram of link 4 from O4 to C to find data of CY4. We get an equation of CY4. We use equation from link 4 to calculate CX. Then we calculate for data dx and dy. In this slide is visual work. We use the data from velocity and acceleration to calculate for torque, and we use that data to calculate for force analysis.
In chapter 4, we talk about Excel calculation. In this slide, we talk about velocity. For velocity, we have 6 points to calculate it. In each point, we have 2 coordinates, x and y. We talk about acceleration. You get acceleration, you have to differentiate second time from velocity for each point and each coordinate of each point. For this slide, we have to talk about angular velocity or omega. We set theta 2 dot to be constant as an input for this mechanism, and we have theta 3 dot, theta 4 dot, and theta 5 dot, and theta 6 dot. We start to calculate the theta dot by find theta prime first. Use future value minus past value of theta and divided by future value of theta 2 minus past value of theta 2, and then you multiply with theta 2 dot, which is 20 radian per second, and repeat this step for all theta, and you will get theta 3 dot, theta 4 dot, theta 5 dot, and theta 6 dot. This slide is show about angular acceleration or alpha. We know that theta 2 dot dot is 0 because theta 2 dot is constant. We calculate theta dot dot by multiply theta double prime with 20 to the power of 2 and repeat this step for all theta.
Now, to find torque, we need to use virtual work equation by inertia times theta dot plus fyg times xg dot over 1000 plus fyg times yg dot over 1000 plus p times yc dot over 1000 and all divided by 20. Now, we need to draw free body diagram and write the force equation to find the reaction force. Resultant force come from remembering the force in the x and y axis, adding the square together and taking the root out.
Okay, the comparison or error percentage. For an equation, we use hand count minus by Excel, then divide by Excel. All of it time with 100, we will get percentage of error. Okay, the theta we use or the input angular is 60 degrees. As you can see here, some of them the percentage error is so small, but some of them percentage error is higher up.
Chapter 6 Summary. In our examination of drum tilting and lifting mechanisms motion, we employ 2 methods to access velocities, acceleration, angular velocities, angular accelerations, and reaction forces for each component of the mechanisms. The initial methods involve graphical and vector analysis through manual calculations, while the second methods utilize the MATLAB's program for motion simulation and Excel for data computations. Upon comparing the outcomes from both methods, we observed notably similar results with minor and major deviations. These variations were attributed to rounding off the decimal points during manual calculations, impacting subsequent calculation that utilized the rounded off results and causing slight deviation from computer calculated results. Importantly, the major deviations were notably influenced by human error in CAN calculation process, emphasizing a significant departure from accuracy. Through the utilization of both methods, we gain insights into their respective advantages and disadvantages. The MATLAB facilitated a visual representation of the mechanism's motion, while Excel expedited the calculation of extensive data employing the same formula. However, the challenge with Excel lay in crafting precise formulas that accommodate various data scenarios. On the other hand, manual calculation proved to be more intuitive and easily amendable.